In this section, we talk about decidability and the recognizability of languages. We have a lot of topics to cover today, but essentially, the other topics are used to prepare you for two tasks: prove a language is decidable and prove a language is recognizable. Now let's look at those tools and definitions. In real life, we like to talk about problems. Given a problem, do I have a solution to it? If I do, what is that solution? And how do I compute the solution? When we talk about computational problems, there is no unique way or universal way to define them. This is kind of cumbersome because we need to define specific terminology for each problem. So for convenience, we transfer those computational problems into equivalent language acceptance problems. For language problems, we only need to take care of two things. Is the input string in the language, or is it not in the language? Now we use two examples to show you the transition. The first example, we want to know whether a DFA accepts an input string W or not. To solve this, we need to run the DFA on W and see whether it enters an accept state or a reject state. If we formulate this problem in the language acceptance problem, it is a DFA. The member strings of this language is a string containing both the DFA and the string W. You might think, how can a DFA, a machine, be an input string? Well, we can encode the machine using alphabet symbols, so long as you have a consistent way to encode. For example, I use 1 to represent state Q1 and use 11 to represent state Q2 and use 1011 to represent transition from Q1 to Q2, and so on. Once we have the coding, we can turn machines into strings. Now the problem of testing whether a DFA B accepts an input string W is the same as the problem of testing whether BW is a member of the language ADFA. B accepts W if and only if BW is in language ADFA. Similarly, if we want to test whether two DFAs are equivalent, we only need to check whether AB is a member of language EDFA. With this transition, from now on, we only talk about language acceptance problems. There are classes of languages defined by Turing machines. One is decidable languages, and the other is recognizable languages. A language L is Turing decidable if there is a Turing machine M such that if W is in L, then M enters accept state when running on W, i.e. M accepts W. And if W is not in L, then M enters reject state when running on W, i.e. M rejects W. Remember that both accept and reject state are halting state. Computation stops immediately after the machine enters either of these states. So for every possible input string W, M halts on it and distinguishes whether it is a member of L or not. M always gives the result. This is a nice property, but not all languages have this property. For example, a language L is Turing recognizable if there is a Turing machine M such that if W is in L, then M enters accept state when running on W, i.e. M accepts W. But when W is not in L, then M might enter reject state or might loop. By looping, the machine does not stop. It runs forever. You might ask, how do we know the machine is looping? The answer is, we don't know, and it's a problem. You might ask, if we don't know the machine is looping, then how can we tell a string W is not in L? The answer is, so long as the machine does not accept W, so long as M does not stop and give you an acceptance answer, W is not in L. If W is in L, M will stop in a finite amount of time and give you an answer. Okay, with the definition of decidable and recognizable languages, let's review the language hierarchy. In the innermost set, we have regular languages defined by DFA, NFA, and regular expressions. The class of regular languages is a subset of context-free languages, which are defined by context-free grammars and push-down automata. Higher in the hierarchy is languages defined by Turing machines. In this level are decidable languages and recognizable languages. Especially, all decidable languages are also recognizable. We will analyze more on these two classes of languages in a few minutes. Now let's turn to universal Turing machines. Regular Turing machines receive an input string and run on this string directly, while a universal Turing machine U receives as input an arbitrary Turing machine M and an arbitrary string W and simulate the behavior of M on W. In other words, U runs M on W. MW is the input to U, and W is the input to M. If M accepts W, then U accepts MW. If M rejects W, then U rejects MW. And if M loops on W, then U loops on MW. I bet you are curious how you can do this. You can think of U has 3 tapes, each with a head. The first tape contains M's tape content and M's head position. The second tape contains M, and the third contains the current state of M. U first finds on the second tape the move corresponding to the current state of M and the symbol under the head for M. Once it finds it, it performs the required action on the first tape. For example, move left or move right or change the symbol under the head, and puts the new state on the third tape. The simulation continues until the current state of M is a halting state. If you don't understand this working mechanism of U, it's okay. You only need to know that U as a Turing machine can run another Turing machine M on M's input. With this property, universal Turing machines are often used in proofs of construction. Okay, now we have all the tools we need. Let's use them by checking some decidable and undecidable languages. L1 and L2 are decidable. In L1, we want to check whether a Turing machine M has 10 states. That's doable, right? We only need to count the states in M. In L2, we want to check whether the input string to a Turing machine is of the correct format. This is also doable. With a predefined syntax, we only need to check each component of W and see if it violates some rules. When I say doable, it's just my intuition, not a proof. To prove a language is decidable, we usually do it by construction. We'll talk about the proof later. Now let's check the other two languages. They are undecidable. The first one is the well-known halting problem of Turing machines. In language ATM, we want to check whether an arbitrary Turing machine M accepts an arbitrary input string W. Intuitively thinking, if M accepts W, then we can tell it because M stops. But if M doesn't accept W, we have a problem, because M might loop on W. In this case, we don't know whether M will stop in a little bit later or M actually runs forever. It's like you sit in front of your computer, waiting for your Java or Python program to stop. After you had a cup of coffee and replied all your emails, you get bored, but your problem still hasn't finished. At this point, you are hesitant whether you should terminate your problem manually because you don't know whether it's gonna finish in the next second or it's into an infinite loop. And actually, at every time point, you have this concern. So you can't just easily terminate the problem. We will talk about this halting problem in later sections. And actually, this halting problem causes many languages to be undecidable. Now, another undecidable language, L3, checks whether a Turing machine enters its start state again when running on W. Still, if M halts on W, it is easy to tell. But if M loops on W, then we might don't have an answer for it, which makes it undecidable. My reasoning here is just my intuition. For a formal proof, we usually need to use reduction or diagonalization. That's a topic for later sections. Now let's prove a given language L is decidable by construction. We construct a Turing machine that decides L. Here we only use high-level descriptions and don't consider the details of state diagrams. We can either construct a regular Turing machine M, which runs on its own input string directly, or we can construct a universal Turing machine M, which runs another machine D on D's input. If the input to M contains another machine, then use this machine when running. Sometimes, even though M does not receive any machines as its input, M can construct another machine as needed. Now let's see a simple example. Let's prove the language L with the member string MW satisfying that M halts on its input string W in 5 steps or less. Note that this M is a general Turing machine and this W is a general string. We construct a universal Turing machine U that decides L. The reason we use a universal Turing machine is that the input to our machine contains another machine M, and we need to check the results of running M on M's input. It doesn't mean that whenever the input contains another machine, we need to use a universal Turing machine. It is not the case. The major reason is that we need to run M on its input. In some cases, even if the input contains another Turing machine, you don't need to construct a universal Turing machine. An example is L1, which takes M as input and checks how many states M has. In this case, we don't need to run M on its input, so we can construct an ordinary Turing machine to decide it. Alright, back to our language, L. This is how I construct U, and you should use similar format in your homeworks if you are asked to construct a Turing machine. although the details will differ. First, I specify the input to U, which is MW, because a member string in L has this format. Then in the body, I give the details. A member string in L requires M to halt on W in 5 steps or less. So we need to run M on W. And we need to keep track of how many steps M has run. So I use a counter I and a loop to run M on W for I steps. In each iteration, I only run M on W for I steps, even if after I steps, M does not halt. After running M on W for I steps, I check whether M halts. To do so, we only need to check whether M enters accept state or reject state after I steps. Once you know how to check whether M halts or not, you can omit the details of how you check it exactly, but just keep the high-level description. If M halts, then we know that M halts on W in 5 steps or less, because I is always less than or equal to 5. If M does not halt in the current iteration, then we increment the counter and go to the next iteration, where M can run more steps on W. We only need to run this loop for at most 5 iterations, because if M halts within 5 steps, you will detect that and accept the string MW and thus halt. If after 5 iterations, you has not given an accept answer, that means M does not halt on W in 5 steps or less. Knowing this, you can reject MW and halt, because this means MW is not a member of L. That's all for this machine. In summary, U is a universal Turing machine. It uses another machine M, and M is given to U as input. And U is a decider because on every input, it always gives an answer in a finite amount of time or steps. One important note, when you write loops, you need to use proper indentation or use braces. If there is a confusion when we grade your homework, we will assume you used the wrong one. Now let's practice with another example. Prove the language NEDFA is decidable. Member strings of this language are DFAs that accept at least one string. In other words, the language recognized by A is not empty. In this example, I want to show you that we can take advantage of other languages that are known or proved to be decidable. In the textbook, page 196, language EDFA is proved to be decidable. So there exists a Turing machine that decides EDFA. Let's call such a machine T, and we use it in our machine U. Now I show you how I construct a decider U that decides NEDFA. First, I specify the input to U, which is of the same format as the member strings in the language NEDFA. Then in the body, I construct a machine T that decides EDFA. Here I omit the details of how I construct T because they are given in page 196 of the textbook. If no such details are given in the textbook or in the class notes, then you need to specify the details how you construct a machine here. After I have constructed T, I run it on A. If T accepts A, then that means LA is empty. So you should reject A. Otherwise, LA is not empty, and you should accept A. Note that T is a decider. It either accepts or rejects its input, and it never loops. So you will either execute the if branch or the else branch and always give an answer. That's all for this machine U. In summary, U is a universal Turing machine. It constructs another Turing machine in it and runs this constructed machine. Another important message: when you use existing deciders, make sure you only use those machines in the textbook or in the class notes, not some machine you find online. If there is some machine you want to use, but it is not described in the textbook or the class notes, then you need to provide the details to construct it, similar to those examples in the textbook. I hope you know how to construct machines after these two examples. Now let's analyze the homework problems. In homework 11, question 1 asks you to prove the language 1DFA is decidable. To do so, you need to construct a Turing machine that decides it. Here are some hints to help you construct this machine. Given the machine M, you need to check whether the language defined by it contains another language as a subset. This 1 star is a regular expression. Do you have some machines for it? Also, how do you check whether a set is a subset of another? What is the relationship between the left statement and the right statement? Since M is also a DFA, so do you have some machine for this language intersection? Finally, we used the knowledge that eDFA is decidable in our last example. Can you apply this knowledge in this example? If you are still kind of confused, I recommend that you read the proof of theorem 4.5 in page 197 of the textbook. Now let's analyze the second homework problem. Is there a Turing machine M satisfying the following condition? The machine M halts on each input string W, and it accepts W if and only if there is a proof of P equals MP. First, if this M exists, it needs to be a decider because it halts on every input string. Second, you don't even need to know the meaning of P equals MP. You only need to know that it is some proposition that is either true or false. So you can analyze these two cases separately. If P equals MP, what is the language of LM? Is this language decidable? If so, construct M. If not, argue why. And you do the same thing for the case where P is not equal to MP. What is the language LM in this case? Based on this knowledge, you either construct a decider for it or you argue this language is not decidable. Alright, you will see hints on problem 3 a little bit later. Now let's move on to another topic, recognizable languages and unrecognizable languages. Recall the definition for recognizable languages is that there exists a Turing machine that can recognize the language. We will talk more about it with the examples. For now, let's just have a look at some examples of recognizable languages. Previously, we talked about that ATM, the halting problem, is not decidable. Now we say it is recognizable. This is not a contradiction. Recall the language hierarchy. The class of decidable languages is a subset of the class of recognizable languages. All decidable languages are recognizable, and some undecidable languages are recognizable, like ATM. We will prove it is recognizable in next slide. In L1, we want to check whether an arbitrary Turing machine uses a finite number of tape cells when running on an arbitrary input string W. In L2, we want to check whether the language defined by an arbitrary Turing machine has more than 10 member strings. These three languages are recognizable. A similar language to L2 is L3, in which the language defined by an arbitrary Turing machine has less than 10 member strings. This language is unrecognizable. You might think why the direction of the comparison gives such a big difference. Well, intuitively thinking, if we can find 11 strings in Lm, then we can safely say that M belongs to L2. But for L3, since there are infinite many strings, if we haven't found 10 strings, we cannot say for sure that the remaining unchecked strings are not in Lm. Of course, if you find 10 strings, you can say M is not in L3. But if we only find 9 strings, we cannot claim that M is in L3, because we cannot guarantee the next string we check will not be in Lm. Again, this is just intuitions. Formal proofs usually use reduction or diagonalization. You don't need to worry about it now. Now I want to prove ATM is recognizable by constructing a Turing machine U that recognizes it. First, I specify the input to U, which has the same format as member strings in ATM. In the body, I will show you two ways to specify U. Let's check the top one first. I use a for loop. In each iteration, I run M on W for I steps. If M accepts W using I steps, then U accepts MW. If M rejects W using I steps, then U rejects MW. If we see neither of them, then go to the next iteration, where M can run more steps on W. Note that U might go into an infinite loop if M loops on W. In this case, U loops and never gives an answer. But it is okay because in this case, MW does not belong to ATM. So long as U does not accept MW, we don't care whether U rejects it or loops on it. An equivalent machine is described below. In the body, I don't even bother to use a loop, because I only need U to correctly accept when the input is a member of ATM. So I just run M on W. If M accepts W, then U accepts MW. If M rejects W, then U rejects W. If M does not give either of these two answers, then that means M loops on W. In this case, U also loops and never gives an answer. But it's okay because when M loops on W, MW is not a member of ATM. In this case, U doesn't have to give an answer. Again, for a recognizer, it only needs to accept strings that are in the language. It doesn't need to explicitly reject strings that are not in the language. Now that we have both constructed deciders and recognizers, let's compare them. For a recognizer, you only need to correctly give an accept answer for input strings belonging to the language. For a decider, you need to correctly give an accept answer for input strings belonging to the language and correctly give a reject answer for input strings not belonging to the language. I'll recommend you use L1 and L2 in the previous slide as practice. How do you construct Turing machines to recognize them? For L1, you probably need a counter. L2 is tricky. You need to list all possible input strings in lexicographical order and use a counter I. Then in each iteration of a loop, run M on the first I input strings for I steps and check whether any of them is accepted by M. If you have no idea what I just said, that's fine. Don't worry about it. Now it's time for hints on problem 3 of homework 11. A language L is co-recognizable if its complement L bar is recognizable. Let A and B be disjoint co-recognizable languages. Show that there is a decidable language S such that A is a subset of S and B is a subset of S complement. This problem asks you to explicitly give the decidable language satisfying the conditions. You either describe this S in terms of set properties like the examples I gave for decidable languages, or you define a decider for it without specifying the specific properties like those in the examples. I recommend the latter. To define such a decider, you first need to figure out some general properties of S. You should analyze each condition given in the problem. For example, A and B are disjoint. Then what is the value of A's complement union B's complement? And A and B are co-recognizable languages. Then what about A's complement and B's complement? What class of languages do they belong to? Do you have Turing machines for them? Since S needs to satisfy 3 conditions, you can use these 3 conditions to help you build up the decider. If B is a subset of S complement, then what is the relationship between B's complement and S? And remember that the machine you construct should be a decider. If W is in S, then you should accept W. If W is not in S, then you should reject W. How do you achieve this with your answers to previous questions I raised? And in the final step of your answer, you need to argue why all the 3 conditions are satisfied with your definition of the machine. This concludes my recitation today. Leave a comment if you have any questions.